So let's start to talk about the first topic of CS61C, which is number representation. It's a very important topic as it's a fundamental thing throughout all the different other topics that we teach. So we have all grown up knowing and loving base 10 numbers, probably because most of us have 10 fingers. But different cultures have historically settled on using other bases to represent their numbers. For example, the Mayans actually used base 20, the Babylonians used base 60, and sometimes we wish we were using base 12, if you're one of those silly Americans, like myself, who prefers inches and feet to centimeters and meters. Side note, I actually do prefer centimeters and meters, but whatever. Went for the joke. even base 60. I mean, how many seconds are there in a minute? How many minutes are there in an hour? How many hours are there in a day? I mean, if only we could have 60 hours in a day. I could have 3 whole naps in just one day. But computers are built around base 2. Do you have any idea of why that might be? Well, really, signals can take on any value. So if you had to define values from 1 to 10 within your range, and then your voltage sources wobbled a little bit, what could happen? Well, you could get a value that is incorrect for what it should have been. If we were in base 10, we would wonder if we meant 9 or 10, for example, if it was like really high. Like maybe it was at 89%. Who knows? It could have been 9 or 10. In binary, we just know which side of 50% we're on. So we have a much wider range of error that we have, so it's less of a probability that we're going to have some corruption. But how do we interpret and understand numbers in different bases? Really, you already know the formula for evaluating numbers even if you don't realize it yet. If I showed you this base 10 number, 9,472, you would tell me that the 2 is in the 1's place, the 7 is in the 10th place, the 4 is in the 100th place, and the 9 is in the 1000th place. We can start breaking down this number and expanding it into the different places that it has. We can even then pull out some values from this. We can pull out the 1000 from the 1000th place. We can pull out that full place. The 100 from the 100th place, the 10 from the 10th place, and the 1 from the 1's place. And if you look really closely, these are actually all powers of 10, which is our base. And since we restrict the value each digit can actually have from a range of 0 to 9, we know that there is a unique representation for every integer as a sum of powers of 10. This might motivate us to postulate a general formula for an arbitrary number of n digits in an arbitrary base b, which is represented as a string of digits d, where instead of multiplying the value of each digit by some power of 10, we multiply each digit by a power of the base b, as seen on the slide. Of course, in order for us to maintain a unique representation for each value, we must have exactly b acceptable symbols for each digit, which takes values from 0 to b minus 1. Further notice, the digit is not really the right term anymore, since it comes from the root meaning fingers, which implies a base 10, which of course we're not necessarily using now because we're using base b. We might use other words to represent different bases, as you will see in the following examples. So in this class, we mostly want to use decimal since that is what we are used to, binary since that's what computers use, and hexadecimal, which is hex for short, since no one wants to read a long string of zeros and ones. It's fun once, but trust me, only once. Notice that in binary we are only allowed to use 0 and 1 for our digits, which in this case are called bits. Notice that in hexadecimal, we need to represent numbers 0 through 15 with just one symbol. So we actually use the letters A through F, typically capital, to represent the values 10 through 15. You can see a summary of representations of natural numbers in the 3 bases in the table to the right on this slide above me. But there is no need to spend effort actually memorizing this. If that doesn't make sense though, you should definitely come to office hours and we'll try to help explain it a little bit better. One more thing is, notice that we will denote which base we are using in the prefix of the number. So we typically do nothing for base 10, we do 0b for base 2, and we do 0x for hexadecimal. This is all because it's really annoying to have to write a subscript after the actual number saying this is base 2, this is base 10. So this just makes life a lot easier for you. And during the discussion that you'll have, you'll actually get a lot of practice converting between the different bases. So another side note that I do want to say is, if you thought a binary bit is fun, well, hexadecimal calls each digit a nibble. So let's actually walk through a quick example. So I want you to try to convert this value 0B11110 to decimal. Is it A, 11, B, 30, C, -2, D, I'm so lost, I mean, that's me sometimes, and E, who even cares about this? I sure hope you care about this. You're going to break our hearts. I'll give you a second or so to actually think this over. Okay, that second's enough, I'm bored. Okay, so let's actually start breaking this value down. So we're in binary, which is base 2, so that means each of the digits, or each of the bits, is going to be something times 2 to the whatever place it's in. So in our case, we can see that we have a 0 in the ones place, essentially. So 2 to the 0 times 0 is 0, so we don't really care about that value here. Then we see the next bit is a 1, so we have 2 to the 1 times 1, which means we keep it, which is just 2. So we have 2 right now as a running sum. Next, we have this digit, which we see as 1, which is 2 to the 2, which is 4. So we're actually going to keep this value as well. So now we have a running sum of 6. The next digit, which is also 1, which means we're going to actually keep this again, is 2 to the 3, which is 8. So we're going to have a running sum of 14. Finally, our most significant digit right here is also 1. So we're going to keep 2 to the 4, which is 16, which means we have a running sum of 30, which means 30 is the correct answer to this problem. Let's go over some of the other answers so then you can understand how it's really easy to actually eliminate some of these choices. -2, I mean, after all, we haven't represented anything that has a sign in it, which means that -2 does not make any sense right now. And also 11, there's actually a trick to this one. The last digit is a 1. The last digit represents 1, but the thing is in our number here, we see that that's a 0. So we can quickly eliminate any odd numbers because we see that the number must be even. That's a very nice trick if you want to quickly look to see if a number is approximately right, at least even or odd, correct. But you might be asking yourself, what does it all mean? What if I presented you with an entire memory of your computer in just zeros and ones and asked you to interpret it? What does it mean? I mean, it's just one super long natural number, isn't it? Or is it a string? I mean, it could be anything, right? This next point is very, very important, and you should really pay attention to this. I mean, like, mentally prepare yourself. It's a good one. Bits are bits. They can represent anything. And it all depends on your interpretation of whatever you want to represent is. For example, we can represent characters. I mean, we have 26 letters, right? So that's 5. That would take us 5 bits because if we have 26 letters, 2 to the 4 is 16, so that wouldn't represent them all. But 2 to the 5 is 32, which means that we could represent all of those characters plus more. What about if we want to add uppercase and lowercase plus pronunciation? Wow, 7. That would require 7 bits, and ASCII is actually the representation for this. How about logical values like true or false? I mean, 0 is typically off, so why not make that false? 1 is true, so why not make that 1 is on, so why don't we make that true? How about if we want to represent students in this class? Well, we have approximately 330 students, which would mean we'd need about 9 bits to actually represent every student in this class. How about colors? I mean, couldn't we just make red 0, green 0, 1, blue 1, 1? Then we'd be able to represent 3 different colors with just 2 bits. There's only one important constraint that you might have noticed that I've been talking about throughout each of these different representations or interpretations of the bits that we had. It's that with n digits for some base b, we can only represent b to the n things. Each of the n digits is one of b possible symbols. That's the other important thing to understand. Do you have any more things than that? Well, you could just add more digits. But how do we assign values to the binary numbers available to us? For example, if there are 3 bits, then we have 8 different bit patterns to define. And with those 8 patterns, we can define those values literally however we want. For example, let's look at this circle here of the different values that we have with just 3 digits. So I want to start making them, I wanted to start assigning them different values. So let's just make 0, 0, hello world, the string hello world. 0, 1 can be the symbol pi, 0, 1, 0 could be unicorn, 0, 1, 1 could be 2, and 1, 0, 0 could be negative infinity. All we have to do is just build the hardware and software around this to be able to interpret this as we want. We could choose to interpret these bit patterns as the first however many natural numbers in binary. And this would actually give us a representation called unsigned integers, which is something that we actually do use. Also, a little note about this comic. Remember that just because we study certain canonical methods of assigning values to binary strings doesn't mean that those are the only options available to us. This really means the largest unsigned integer is not necessarily the largest representable number. So let's continue with our 3-bit example for unsigned integers. In our 3-bit example, here are the numbers you'd actually get if we interpret it as unsigned values. Now, with an arbitrary n bits, how do you think we'd actually represent 0? I mean, that would just be all zeros. How about the most negative number? Well, we're unsigned, which means we can't represent negative numbers, so the most negative number is still 0, which means it would be all zeros. How about the most positive number? Well, that's just all ones, which means that we could represent values up to 2 to the n minus 1 in base 10. How do we increment these? Well, the same way how you would normally increment it with like long addition of 2 positive numbers in decimal. Only if you ever reach the number 2, that is the time when you actually carry that value over. Notice that adding 1 to an unsigned integer always results in a larger, more positive number, with an exception where we overflow where it's like 1 plus all ones. So what happens when I would add 1 to 7 in this case? Well, the number that we'd get would be 0. So what if we need to represent more positive numbers? Well, as long as they're not too big, we can add additional digits. What if we need to represent negative numbers? Well, sadly with unsigned integers, we actually cannot represent negative numbers. That's where the next topic that we'll go over will be signed integers, which will explain how we actually how we represent negative values.